Okay, thank you. Okay, well, this is, I guess, our makeup video number 2. And so hopefully we'll be back up to speed by the time we're done with this. And where we left off was in chapter 16, acid-base theory. We're talking about conjugate acid-base strength. And because we're often talking about weak acids and bases, it's a situation where basically all strong acids and bases are more or less equally strong, but there's a huge variety of strengths among weak acids and bases. Some are stronger than others, some are weaker than others, but they're still all weak because they still ionize way less than 100%. But there can be quite a bit of difference in terms of their relative strengths. Well, the same is true of conjugate acid-base pairs. It turns out that the stronger, say, the acid is, the weaker its conjugate base is. And the weaker an acid is, the stronger its conjugate base is. And the same for bases. The stronger a base is, the weaker its conjugate acid is, and vice versa. And so coming back to the fact that when we say that an acid is strong or weak, we're basically referring to its percent ionization. If its percent ionization in water at the given temperature is 100%, then it's a strong acid or a strong base. And if it's much less than 100%, then it would be considered a weak acid or base. And the funny thing is that with acids and bases, it's pretty much all or almost nothing. You'll find strong acids that ionize 100% in water, and then you'll find weak acids and bases that you hardly ever ionize more than maybe 10%. And there's really not much in between. So like I said, it's kind of all or nothing, or almost nothing. Okay, so strong acids, like I said, 100%, and they're all more or less equally strong. And for weak acids and bases, the dissociation is way less than 100%, but the percent dissociations will vary from one weak acid or base to another. And they will also, the percentage dissociations of weak acids or bases will also vary with the temperature, because it's an equilibrium reaction and temperature affects equilibrium reactions. And also the concentration of the acid or the base will affect its percent dissociation if it's a weak acid or base. Okay, so, and as I said, conjugate bases of weak acids and conjugate bases of weak acids and conjugate acids of weak bases also have different relative strengths versus each other and versus their conjugate partners. Okay, so as I said before, a strong acid, for example, HCl, has a very weak conjugate base. Chloride ion is a very weak base as bases go. And that's as opposed to hydrochloric acid, which is one of the strong acids. A strong base, like say hydroxide ion, which you could get from any of the strong acids, sodium hydroxide, potassium hydroxide, barium hydroxide, whatever. It's the hydroxide ion itself that's basic. And the hydroxide ion is the strongest base there is. And if you look at the conjugate acid of OH minus, it is in fact H2O, water. Water, of course, is very weak as an acid. In fact, water itself is generally not an acid at all. It's neutral. And that's pretty weak at being an acid. The only time water can act as an acid is if you put a base into the water. The base kind of forces water to act like an acid, but it doesn't really want to. So this strong base hydroxide ion has a very, very weak conjugate acid. A weak acid like hydrofluoric acid actually has a relatively strong conjugate base. Fluoride ion is relatively strong. It's still weak, but it is relatively strong as a base. As relatively strong as a weak base. A weak base, like say ammonia, has a relatively strong conjugate acid, which is the ammonium ion. It's still a weak acid. Ammonium ion is a weak acid, but it's relatively strong compared to the other weak acids, whereas ammonia is pretty weak compared to the other weak bases. And an example of comparing strengths is this problem here, the practice problem 16.4, where it gives you some weak bases, bases that are derived from ammonia in order of their strengths as bases. And you notice that each of them has nitrogen with other stuff attached to it. And that is based on ammonia. Ammonia is nitrogen with 3 hydrogens attached to it. Nitrogen normally has 3 things attached to it. When it has 4 things attached to it, like in the ammonium ion, it'll have a positive charge. But for a neutral charge, nitrogen normally wants 3 bonds. And so if you remove one of those hydrogens and replace it with a methyl group, which is what you call CH3 in organic chemistry, you get what's known as methylamine. So amines are compounds that are based on ammonia. So NH3 is ammonia, CH3 replacing one of the hydrogens, leaving the other 2 hydrogens on the nitrogen behind, would be methylamine. And if you replace one of the other remaining hydrogens with another methyl group, you get 2 methyl groups, an N and an H, and that's known as dimethylamine, because 2 methyl groups, dimethylamine. And so the question is, what would be the conjugate acids and what are their relative strengths? So right away, you know, if the base strength goes this way, then the strength of the conjugate acids is going to go the other way. So the conjugate acid of NH3 will be the strongest, and the conjugate acid of dimethylamine will be the weakest. But first of all, what are the conjugate acids? Well, the conjugate acid is what you get when you add an H plus to what's already there. That's all you have to do. That's how you can tell the difference between a conjugate acid-base pair. They only differ by an H plus. And so if you want to go from a conjugate base to a conjugate acid, add an H plus. So NH3 becomes NH4 plus, and CH3NH2 becomes CH3NH3 plus, and CH3 to the quantity 2, NH becomes CH3 to the quantity 2, oops, left something out, NH2 plus. Okay. And notice that the order is indeed the opposite of what it was for the bases. So the conjugate acid of NH3 is NH4 plus, that's the strongest. The conjugate acid of dimethylamine is dimethylammonium ion, is what you call that. CH3 NH2 plus, that is the weakest, and methylammonium ion is what you call this, and that is in the middle, like before. So it's the opposite order. Just briefly, one of the advantages to the Brønsted-Lowry theory over the Arrhenius theory is that the Brønsted-Lowry theory can actually apply to situations that are not in water. And generally, we consider it that in order to be an acid or a base, something pretty much has to be in water. But the Brønsted-Lowry theory is broad enough that it can actually be applied to situations where no water is present. And one of the examples cited by the book is the gas phase reaction between hydrogen chloride, which, remember, if it's a gas, it's called hydrogen chloride because it's not technically hydrochloric acid unless it's dissolved in water, and ammonia gas, which actually has the same name as a gas as it does when you dissolve it in water. And from that, you get ammonium chloride, which is a solid. And actually, you can actually, interestingly, observe, maybe we'll try it in lab if I remember it. And if I don't, you can remind me. It's kind of cool because you can see this reaction happening. All you have to do is take a bottle of concentrated hydrochloric acid and a bottle of concentrated ammonia and, in solution, and put them on the bench next to each other. And since hydrochloric acid is just hydrogen chloride gas dissolved in water, it will be giving off vapors of hydrogen chloride gas because some of the gas gradually comes back out of the water. Same with ammonia. Ammonia in solution is just ammonia gas dissolved in water. And of course, if you've ever used ammonia for cleaning, that gives off fumes big time. And so the 2 bottles will be giving off fumes sitting next to each other. And in the middle where those fumes meet, you see this sort of white cloudy substance forming. And that is little particles of ammonium chloride that are forming in the air. And they're so small that they keep floating in the air and they don't come raining down. But it's still a pretty cool thing to see. Anyway, in this reaction, hydrogen chloride is donating a proton to ammonia because ammonia is becoming ammonium, which is part of this molecule. Okay, so that makes hydrogen chloride a Bronsted-Lowry acid. And the ammonia is gaining a hydrogen, NH plus ion, making it a proton acceptor. So ammonia is acting as a Bronsted-Lowry base. And both of them go together to form one product. This is a synthesis reaction. So there's only one product. And so it ends up that ammonium chloride is both the conjugate acid and the conjugate base of both of the reactants. Okay, so it does sometimes apply to situations that are not in water. An important concept for when we get into talking about pHs and things like that is the fact that water actually does ionize to a small extent. And we think of water as a covalently bonded compound or a molecular compound, and not an ionic compound. And that is true. Water is a covalently non-ionic type compound, but as we saw with acids, covalently bonded compounds can sometimes ionize. And the fact is that water itself does ionize to some extent. Even when nothing else is present, the H2O molecules will ionize to some extent into H plus and OH minus, which is the reaction that's shown right here. H2O can dissociate into H plus and OH minus. Or if you want to show it the way with H3O plus ions instead, it would be like this. You need two water molecules combining and dissociating into H3O plus and OH minus. And this is known as autoionization. That is, water ionizes with itself, not in the presence of anything else. And this always happens to some extent under any circumstances, even when you just have pure water. Now, the fact is that in pure water, the equilibrium lies very much to the left. And so in any situation where you have pure water, a vast, vast majority of it will be present as intact H2O molecules, not as H plus or OH minus. Probably, in the area of 99% of it plus will be H2O rather than H plus and OH minus. But even in under situations like higher temperatures, where the water will dissociate to a greater extent, it doesn't really matter because it will remain neutral, because for every H2O molecule that ionizes, you get an H plus, the characteristic ion of acids, and you also get an OH minus, the characteristic ion of bases. So in terms of whether the solution is acidic or basic overall, they cancel each other out and it's still neutral. Okay, so this is an equilibrium reaction. The reverse reaction is very much favored at room temperature and even more so below room temperature. If you raise the temperature, you can get the reaction to shift a little bit to the right, but still the reverse reaction would be favored. And the KEQ for this reaction, because it is an equilibrium reaction, the KEQ for the reaction is, in this case, it's given a special name, KW, which just stands for the equilibrium constant for the autoionization of water. But it is an equilibrium reaction, and so we form the equilibrium constant the same way we would for any other equilibrium reaction. It's products over reactants. And so we have equilibrium concentration of H3O plus times the equilibrium concentration of OH minus, and we don't divide it, in this case, by the equilibrium concentration of the reactants, because the reactants are pure liquids, and pure liquids do not appear in equilibrium constant expressions. So that's it. That's the KEQ for the autoionization of water. And it turns out that in pure water, since every H2O molecule that ionizes will produce an H plus and an OH minus, these two numbers would be equal to each other in pure water. And it turns out that the H3O plus concentration in pure water would be 10 to the minus 7 molar. And the OH minus concentration in pure water would also be 10 to the minus 7 molar. And 10 to the minus 7 times itself is 10 to the minus 14. And so the Kw, or that is the equilibrium constant for the auto-ionization of water, is 10 to the minus 14 at 25 degrees Celsius. And so this is actually always true. And it's interesting that this is not just true for pure water, but it's true for any aqueous solution, as it turns out. If you add acid to the water, the H3O plus concentration is going to go up, but the OH minus concentration will go down. And so one times the other will still be 10 to the minus 14. So it's not just always true for water, it's also true for any aqueous solution. You know, if you add a base, the OH minus concentration is going to go up, but the H3O plus concentration is going to go down. And one times the other is still 10 to the minus 14. So that's something that's kind of important to remember, because that's true of any aqueous solution at 25 degrees Celsius. Okay, and so this is why water is pure water is considered neutral, because the H3O plus and OH minus concentrations are equal to each other. And to illustrate just how far to the left this equilibrium is shifted under normal conditions, at 25 degrees Celsius, you can, if you want to, figure out the molarity of pure water. It's kind of an unusual idea, because in molarity, you're usually looking for the concentration of a solute, and all we have here is pure solvent. But molarity is number of moles per liter, right? And there's no reason you couldn't figure that out for pure water. How many moles of pure water are there in 1 liter of water? And the answer is 55.6. So the molar concentration of pure water is 55.6 molar. And when it dissociates into ions, you'll have 10 to the minus 7 H3O plus, that's 0.000007 H3O plus, and the same concentration of OH minus, and the remaining water will be 55.5 minus 10 to the minus 7, which is 55.6 or 55.5, whatever I said. So in other words, the ionization of water takes so little away from the original concentration of the water that you won't even notice the difference within a reasonable number of significant figures. And so we generally consider, for most purposes, we consider the concentration of H3O plus or OH minus in pure water to be effectively 0. I mean, we know it's 10 to the minus 7 actually, but unless we're dealing with very, very dilute solutions and we need to be extremely accurate, it's usually close enough just to say good as 0 for both of them in pure water. Okay, so, okay, I already mentioned that, and I mentioned that. So whether the solution is acidic or basic really comes down to which concentration is bigger, the H3O plus or H plus, if you like to think of it that way, or the OH minus. If the H plus concentration is bigger than the OH minus concentration, then the solution is acidic. And we know that if one goes up, the other has to go down by the same factor, because they both have to multiply out to 10 to the minus 14. So if one of these goes up, the other is going to go down. So it's going to be fairly obvious which one is bigger. And because the cutoff point, or say the point where everything is even, is 10 to the minus 7 molar, and for an acidic solution, you would expect H plus to be greater than 10 to the minus 7, and the OH minus concentration to be less than 10 to the minus 7. And you have to be careful here, though, because we're dealing with negative exponents. So for example, 10 to the minus 8 is smaller than 10 to the minus 7. 10 to the minus 5 is bigger than 10 to the minus 7 because of the exponents being negative. If the OH minus concentration is bigger than the H plus concentration, then the solution is basic. And so for a basic solution, you'd be looking at an H plus concentration that's less than 10 to the minus 7, or an OH minus concentration that's greater than 10 to the minus 7. Because of course, in reality, and in a basic solution, both of these would be true, just as both of these would be true in an acidic solution. But you might not know both of those facts. So if you find out that either one of these things is true, that right there would be enough to say that the solution is acidic. And if you find out that either one of these things is true, then that means the solution is basic. Okay, addition of H plus or OH minus to the water will shift the equilibrium so that H plus times OH minus still equals 10 to the minus 14. And that's because, again, of Le Chatelier's principle. The equilibrium for the dissociation of water into ions will shift one way or the other so that you will end up with the same result when you take the equilibrium constant. Okay, so a practical example here might be finding the H3O plus concentration in some solutions like soft drinks that has an OH minus concentration of 7.1 times 10 to the minus 12. Now, I showed you on the previous page that H plus times OH minus, or sorry, yeah, or H plus or H3O plus times OH minus always multiplies out to 10 to the minus 14. And we know that that's always true of any aqueous solution. But that's not the way we usually use that equation, because we already know that this times this is going to be 10 to the minus 14. The way we use that equation is to find either H3O plus or OH minus when we know the other one. And so in this example, we know that OH minus is 7.1 times 10 to the minus 12. But what we want is H3O plus. And so by this equation here, the KW equals H3O plus times OH minus. H3O plus would be KW divided by OH minus, or in other words, 10 to the minus 14 divided by, in this case, 7.1 times 10 to the minus 12. And that gives us 1.41 times 10 to the minus 3. And that would be the H3O plus concentration. That makes sense because 10 to the minus 3 is actually a fairly large concentration when you're dealing with acids and bases. And it's said that what we're talking about here is a soft drink. Soft drinks, almost, well, all of them essentially are acidic to one degree or another. And so you really should come out with a relatively large concentration of the H3O plus ion. Soft drinks tend to be acidic not only because carbon dioxide dissolved in water creates carbonic acid, which makes the solution acidic, but also a lot of them have citric acid in them. Anything that's like orange or lemon flavored or has anything like that in it is going to have citric acid in it. And the dark colas like Pepsi and Coke have phosphoric acid in them. So yeah, they're definitely going to be acidic. And in this case, 10 to the minus 3 is definitely greater than 10 to the minus 7. So the solution is indeed acidic. Laundry bleach, on the other hand, as I mentioned, most cleaners are basic. So we're expecting this solution to be basic, but we have to prove it. The OH minus concentration is 2.9 times 10 to the minus 3. Well, that right there, we can tell because the OH minus concentration is greater than 10 to the minus 7. It's basic. But we also still have to find the H3O plus concentration. That's going to be KW divided by OH minus, which is 10 to the minus 14 divided by the 2.9 times 10 to the minus 3. And that gives us 3.45 times 10 to the minus 12 for the H3O plus concentration. The H3O plus concentration is less than 10 to the minus 7. And that also means that the solution is basic. The fact that H3O plus is less than 10 to the minus 7 and OH minus is greater than 10 to the minus 7, both of those things tell you that the solution is basic. And because H plus and OH minus multiply out to the same thing every time, what that means is that they are actually inversely proportional to each other. It's not just, if you add an acid to the solution, the H plus goes up and the OH minus goes down, they go up and down by the same factor. So if H plus doubles, OH minus is cut in half, that kind of thing. If H plus goes up by a factor of 10, then the OH minus concentration is divided by a factor of 10. All right, so you don't always have a pH meter handy, so sometimes you have to calculate the pH of a solution. And that's what the next section is about, where we find that the H plus and OH minus concentrations are usually pretty small. You know, like I said, 10 to the minus 3 or 0.00141 would be fairly large for an acid concentration, especially in an everyday substance like a soft drink. And because they're small, they involve negative exponents. And dealing with negative exponents can be tricky, like when I explained that, you remember 10 to the minus 8 is smaller than 10 to the minus 7 because of the negative exponent. That gets confusing really easily, and it's easy to get mixed up. So that's the main reason that the idea of pH was developed, because pH has the effect of, for one thing, removing the negative sign, but also acids and base concentrations can involve a huge range of concentrations. You know, you can go in terms of acid concentration or H plus ion concentration, you can go anywhere from, say, 12 molar or so down to 10 to the minus 14 molar. And that is a huge range in terms of the magnitudes of the numbers. And what's often done in cases like that, where you have a huge range of magnitudes to deal with, is that you'll often take the numbers and turn them into a log scale. Because taking the logarithm of the number will give you a sort of a more compact, easy number, and the numbers will span a smaller range of magnitudes. And so that's what they've done with the idea of pH. pH is the negative log of the H plus ion concentration, or negative log of H3O plus if you want. And what that does is it takes the huge range of magnitudes that you can get for H plus ion concentrations and confines it to a range of numbers from about 0 to 14. Instead of, say, about 12 to 10 to the minus 14, you know, a range like this is much easier to deal with. And also, because it's negative log, you end up losing the negative sign. So essentially, in modern scientific calculators, you can just enter the negative sign before the log command. But essentially what you're doing is you're taking the logarithm of the H plus concentration and removing the negative sign. Because the logarithm of something like 10 to the minus 3 is going to be the logarithm of 10 to the minus 3 is minus 3. If you take the negative of that, it becomes 3. So much simpler. Okay, so the negative sign makes pH as positive, but unfortunately, what that means, the negative sign gets rid of the negative sign that you'll get for the logarithm, but it now means that the numbers are reversed. So we often think of pH as being a way of measuring the acidity of a solution, and it is. But unfortunately, the fact that it's a negative log means that smaller numbers are more acidic. So the scale actually kind of goes in the opposite of the direction you'd expect. So lower numbers for pH are more acidic. So the pH range, as I said, spans the range from about 0 to 14. And up to the midpoint, that is up to 7, the solution would be considered acidic. And the further away the number is from 7, the more acidic the solution is. And the closer to 7 the number is, the less acidic the solution is. But it's important to remember here the difference between more acidic versus less acidic versus strong acid and weak acid. Just because it has a pH of 1 and it's very acidic, that doesn't mean that it's a strong acid. It could just be a very concentrated solution of a weak acid. And just because it has a pH of 6.8, that doesn't mean that it's a weak acid. It could just be a very dilute solution of a strong acid. So pH depends not only on how strong or weak the acid or base is, or the acid is, but also what is its concentration. Because the H plus ion concentration that you actually have in solution depends on percent ionization. That's the acid strength, but it also depends on the acid's concentration. So those are two things. So you can't say whether an acid is strong or weak based on its pH. You can just say how acidic that solution is. So 0 to 7 would correspond to H plus concentrations of 1 to 10 to the minus 7. 7 would be the neutral point, and neither acidic nor basic. And that would be an H plus concentration of 10 to the minus 7, and also an OH minus concentration of 10 to the minus 7. And then anything above 7 up to about 14 would be basic, which corresponds to H plus concentrations from 10 to the minus 7 up to 10 to the minus, or down to 10 to the minus 14. All right. So that's kind of a summary of the pH scale. You just have to remember the lower numbers are more acidic and the higher numbers are more basic. And again, it works the same with bases. Just because a basic solution has a pH of 14, that doesn't mean it's a strong base. It could just be a really concentrated solution of a weak base. And just because it has a pH of 7.5, that doesn't mean it's a weak base. It could be just a very dilute strong base. All right, so remember that too. That's important. That's been about half of our allotted time. So I'm going to stop here and continue in a moment with part 2.